All right. So let us continue with understanding, trying to determine when given an operator on a finite dimensional inner product space, it's possible to find a basis consisting of eigenvectors, which is moreover orthonormal. Okay, so remember that's the task. And let me remind you that in the previous lecture we have solved this problem for the field of complex numbers, right? When the field of scalars is the complex numbers. Okay, so let me remind you. Reminder. So we have that for f, the field of real numbers, okay, or equivalently for a real inner product space. Excuse me, for complex inner product. Sorry. For real, that's what we're going to do today. So actually, what we did is for the complex numbers, right? So for f, the complex numbers, equivalently for a complex inner product space, KIPS, we have the following equivalence, okay? And we're assuming also that the dimension is finite. Then we have the following equivalence. So T has, or rather, let me write it like V has, because it's a basis for V, right? So V has an orthonormal basis consisting of eigenvectors for T, right? So we have this. And this happens if and only if T is normal. Okay. So remember, normal means that it commutes with its adjoint operator. So T star is equal to T star T. All right. Okay. So this we already know. But we also know that normality is not sufficient in the case of the field of reals, right? So we had this example in the previous lecture. Let me remind you. So recall, we have the example, namely the rotation operator, right? So remember T from R squared to R squared. So in this case, V is the inner product space R squared with the standard inner product, the dot product. And T is the rotation by angle theta for some fixed theta, right? So by angle theta for theta angle between 0 and pi. So some proper rotation, right? Okay. So in this case, we know that then T is normal. We discussed this last time, but T has no eigenvectors at all. No eigenvectors at all. So in particular, this tells us that there cannot possibly be a basis consisting of eigenvectors for V, right? Because there are no eigenvectors at all. Okay, but this is normal. So what this tells us is that in the case when the field of scalars is the reals, yeah. So when we have a real inner product space, the condition of normality is not sufficient. So normality of T is not sufficient to have the implication from right to left in this equivalence, right? So this part doesn't hold in the case of reals. Normal does not necessarily imply basis of eigenvectors. All right. So this motivates our discussion today. We're trying to find a stronger condition which characterizes orthonormal basis of eigenvectors in the case of real inner product spaces. Okay. So this example shows we need something stronger than normality. Okay, and the answer is actually going to motivate the following important property of operators, the so-called notion of self-adjoint operators. So let's define this definition. So in this case, assume that T is a linear operator on V, okay, where V an inner product space. All right, then we will say that T is self-adjoint Okay, self-adjoint. And in the case when T is equal to T star. So as the name suggests, right, self-adjoint, that is adjoint for itself. So it means T is equal to T star. Okay. And sometimes also in the literature, you can see Hermitian used instead of self-adjoint. Okay, so this is after the name of French mathematician, Hermite. So Hermitian or self-adjoint, but we'll mostly use self-adjoint, I think, terminology. Okay, so you see this is a certain property that a linear operator may or may not have. And similarly, we will also define self-adjointness for matrices. As usual, we have the analogous definition. So we will say that the matrix A, square matrix, n by n, over F, is called self-adjoint. Okay, it's called self-adjoint if we have the same condition. So A is equal to its complex conjugate or to its adjoint as a matrix. Yeah. Okay, so we have this new notion. Let's try to understand how it relates to normality. So the first remark is that it is indeed a strengthening of normality, of being normal. So we have that T is self-adjoint implies that T is normal. Okay, and this of course is straightforward, right? Because look, if we have T equals T star, right? So it implies that T star is equal to T square, and this is the same as T star T. So it's also just T square. So we get that they equal, right? So we see that self-adjoint implies normal, okay? Also, we have that T is, so this is 1, let's say 2. T is self-adjoint if and only if we have that the matrix representing T with respect to beta is a self-adjoint matrix. Okay, for some orthonormal basis. For an orthonormal basis beta. Okay, so we have this, and this again, I think this should be clear, right? Because remember, if we have an orthonormal basis and we look at the matrix representing T with respect to it, right? Because then we have, for such a beta, an orthonormal basis, we know that the matrix representing T star with respect to beta is equal to the adjoint of the matrix representing T with respect to beta, right? And so if T is equal to T star, so we see that the matrix is equal to its own adjoint. Okay, so we have this. That's why we have if and only if here. Okay. All right. So now let's try to understand why this stronger notion might be good for us to answer our question that we're trying to do, right? So to characterize existence of orthonormal bases consisting of eigenvectors. So towards this purpose, we want to do something that similar to what we had in the case of complex inner product spaces. So remember the first very useful condition, the point of working over the complex numbers, how it helped us last time. It helped us because we knew that every polynomial over the complex numbers splits, right? That's what we used. That was the only thing we used about the complex numbers case. Okay, so here we'll try to get the same condition. So we want to use to obtain the same property that we had in the complex case, namely that the characteristic polynomial splits. So now we try to get that given a self-adjoint operator. Okay, and this is the next lemma. So let me write it. So given T, a linear operator over V, where V can be real inner product space or complex inner product space, doesn't matter. So where V is an inner product space and the dimension of V is finite. Okay. Assume that T is self-adjoint. So assume T is self-adjoint. Okay. In this case, we're going to show that every eigenvalue of T is real. Okay. So this is the first claim. Of course, you can tell me if the field is the reals, then it's not saying anything, right? So of course, this is trivial. If V is a complex inner product space, so this is trivial if the field of scalars is already the reals, right? In this case, property 8 doesn't tell us anything new, but meaningful. This is meaningful if we have that the field of scalars is the complex numbers. Because a priori, if we have an operator on a complex inner product space, if it has eigenvalues, they might be complex numbers, which are not real, right? They might be imaginary, for example. So what we get here, in addition, is that they're always real. The eigenvalues of T are always real. When T is self-adjoint, this is one. And part B, so suppose that V is a real inner product space, RIPS, yeah? Real inner product space. So if V is a real inner product space, then the characteristic polynomial of T splits. Okay, so we get the desired conclusion. If T is self-adjoint, then the characteristic polynomial splits, even if we are working over the real numbers, right? So again, the second part B, we know it's trivial over the complex numbers, because over the complex numbers, every polynomial splits. But over the real numbers, this is non-trivial, right? Like it's not automatic. So this is where we use self-adjointness as opposed to just normality. This is the extra that we need to get the theorem over the real numbers. All right. So this is the lemma. So let's try to prove it. So proof. So let's check A first. Okay. So A. So suppose we have an eigenvalue. So let's say we have that T of X is equal to lambda X for some X non-zero in V and some lambda a scalar in F. Okay. So suppose we have an eigenvalue, right? So as we know that a self-adjoint operator is also normal, right? So T is self-adjoint. Then, as we remarked, so also normal, okay? And so we can use the previous theorem. So by theorem, this was theorem 615, part C, I believe. We have the following expression for this vector. So we have lambda x, okay? If it's equal to T of X, but then we know that this is equal to T star of X. And this is where we're using this theorem and the fact that, in fact, sorry, not even the theorem, this is just self-adjoint, right? So T is self-adjoint, okay? So it's simply self-adjointness. T is equal to T star. But now using the theorem, we know that evaluating the adjoint T star on an eigenvector X, it's still an eigenvector for T star with the eigenvalue lambda complex conjugate, right? So we get that T star of X is equal to lambda bar X. Okay, so we have this. But also note, okay, so basically we have this equality. Lambda X is equal to lambda bar X, right? But because X is non-zero, this implies that lambda is equal to its conjugate. So this implies that lambda is equal to lambda bar, right? Because if we multiplying X by two different scalars, we would get two different vectors. But here we get the same. So then the scalars must be the same. And hence, lambda is real. So lambda is a real number, right? Because we know that these are those complex numbers, which are equal to their complex conjugate, these are exactly the real numbers. Okay. So this tells us that lambda is real. And this proves part A. Okay. So now let's prove part B. So let me go back for a second. So we want to show that in the case of a real inner product space, the characteristic polynomial splits. Okay. All right. So to show this, we want to understand the characteristic polynomial. So we want to look at the matrix representing the operator. Okay. So let T, so T is given. Let me not copy it. So let T be, as in the problem, a self-adjoint operator. And let us denote by n the dimension of V. Okay. So we know it's finite. So let's denote it by n. And let beta be an orthonormal basis. Orthonormal basis for V. Okay, so it exists because the space is finite dimensional. And finally, let A denote the matrix representing T with respect to beta. All right, so we have this presentation. Okay, now since T is self-adjoint, the matrix is also self-adjoint. So we have A is self-adjoint, right? Okay. So we have a self-adjoint matrix. So now let's try to look how multiplication by this matrix behaves on the complex numbers. Okay, so namely, let T subscript A, let this be the linear operator on the vector space Cn, okay, defined by Ta of x is equal to A times x. Okay, so we take this for all x in Cn. Okay. However, important point here, in this case, note that the field of scalars is R. Okay, so note that the field, so note that F is equal to R here. Okay, and we look at this operator. Okay, so now let's look, let's try to analyze a bit how this operator behaves. So first of all, we have that TA is self-adjoint. Okay, so TA is self-adjoint because we have that if we look at the matrix representing TA with respect to gamma, this is going to be exactly A, where gamma is the standard basis. So where gamma is the standard ordered orthonormal basis for Cn. Okay. So this we know, of course, because if you look at Cn, the standard basis, it's automatically orthonormal over any field, so in particular over C, for Fn, so in this case for Cn, right? And the matrix is A exactly because our operator is just multiplying by A. So then matrix representing it is exactly A. Okay, so we have this. Now by part A, we know that the eigenvalues of TA are real, right? So we know that the eigenvalues of TA are real, right? So by A applied to TA, and also because this is an operator over Cn, we know that by the fundamental theorem of algebra okay, the characteristic polynomial of TA splits into factors of the form T minus lambda, okay, for lambda an eigenvalue of TA, right? Okay, so this follows because T is over the complex number. So you see we're using this trick that to understand our initial linear operator, which is over the real, over the field of reals, we try to analyze some related operator, which is over the complex numbers. And then we try to get the information about the original one using it, okay? All right, so we have this, but also note that each eigenvalue lambda of TA is real by part one, right? By part A, they're all real. So meaning that lambda is an R, okay? It follows that the characteristic polynomial of TA already splits over the real numbers. So already splits over the reals, right? Okay. So we have obtained this additional information, okay? But also note why this helps with the original question, because we know that TA has the same characteristic polynomial as A, right? And A, remember, the matrix A was defined to be the matrix representing the original operator, T. So we know that A has the same characteristic polynomial as T. Okay. Because of this, we can conclude that the characteristic polynomial of T splits, okay, as wanted. Okay. So this concludes the proof. So we used this trick that we started with the linear operator on a vector space V over the real numbers, right? So we had a real inner product space, but then we defined some related linear operator using the same matrix that we had for T. But now we had the linear operator on Cn instead over the complex numbers. Okay. And then we used and then we used part A to, but the point was that we never changed the characteristic polynomial. Why all this change of the operator, passing to a matrix first, passing to a matrix A, and then taking the associated linear operator TA, the characteristic polynomial was the same on each step. All right. So that was that's why it works. Whoops. All right. So this gives us the lemma. Okay. So, but look, now we're in a good shape because we have obtained that for a self-adjoint operator over a real inner product space, the characteristic polynomial splits. So this means that again, we can apply Schur's theorem, like we did in the case of complex numbers. So the hope is maybe we can run the same proof as we did last time, but now with the stronger assumption self-adjointness, which still gives us the characteristic polynomial splits. So we will get the upper triangular matrix in the same way, etc. Okay. So let's check if this idea works. So this is going to be the theorem, the main theorem, theorem 617. Okay. So the situation is, assume T is a linear operator on V, where V is a real inner product space. Okay, so real is important here, real inner product space. And we assume, as usual, that the dimension of our inner product space is finite. Okay, then we have the equivalence. T is self-adjoint if and only if there exists an orthonormal basis beta for V consisting of eigenvectors for T. For T, okay? So we get again the desired equivalence in this theorem. Yeah, so remember, for complex numbers, instead of self-adjoint, we just had normal here, but now we have to say the stronger requirement, self-adjoint. Okay. Excuse me. So yeah, so let's prove this. Okay, so first let's show the implication left to right. Self-adjoint implies existence of an eigenbasis like this. Okay, so suppose T is self-adjoint. Okay, and by the lemma that we just proved, the part B of the lemma, we know that the characteristic polynomial of T splits. Right, so splits over the field of scalars F, which is the real numbers. Okay, so it splits. But then we can apply Schur's lemma. So applying Schur's lemma or Schur's theorem, depends. So applying Schur's theorem, both phrases are used interchangeably. So this is theorem 614, right? That we proved last time. We can find an orthonormal basis beta for V, such that the matrix representing T with respect to this basis, let's denote it by A. So A is the matrix representing T with respect to beta. So this matrix is upper triangular. Okay, so we get this. Okay, but let's see. So what do we have? So we have the if you look at the adjoint of the matrix of A, so this is the same as the matrix representing T with respect to beta adjoint, right? Because we took A to be that matrix. Now, with respect to this beta, we know that this is the same as T star beta, right? So the matrix representing the adjoint of T with respect to beta. And because our operator is self-adjoint, this is the same as T with respect to beta. Okay, so this is just A. So we have all of this because T is self-adjoint by assumption. Okay, right? So what do we have? So we have that A and A star, the conjugate transpose, are both upper triangular. Right? But what does it tell us? So imagine if both the matrix itself and its transpose are upper triangular, right? So we have like this, everything is below zero. And then if you take the transposition, well, and conjugate as well, yeah, so take the conjugate transpose, then again we get an upper triangular matrix, right? So if you think about it for a second, the only way this can happen, because what was above the diagonal here, in the transposed version, it becomes below the diagonal, right? And vice versa. But the point is that we had zeros here below the diagonal, and then we still have zeros here below the diagonal. So the only way this can happen if the matrix A is actually already diagonal, right? It has zeros everywhere outside of the diagonal. So A must be a diagonal matrix. Okay, but this is quite good, right? Because we know that if we found the basis with respect to which we have a diagonal matrix. So then it's automatic that beta must consist of eigenvectors for T, right? Because A is a matrix representing T with respect to beta. So then it means that if you act by this matrix or by the operator on some vector in the basis, all this happens to it is it gets multiplied by some entry on the diagonal. That's exactly being an eigenvector. So this tells us that we found the basis consisting of eigenvectors. But remember, we chose beta to be orthonormal, right? So here we have orthonormal basis beta. So this means we have proved the right-hand side. So this shows this implication holds, right? Yeah, makes sense to everyone. I'll pause for a second here. Excuse me. Okay, so if this is good, let's try to prove the converse implication. So we need to show that if there is such a basis, then the operator T is self-adjoint. So this time, assume that beta is an orthonormal basis for T. Well, for V, I keep saying this. So basis for V consisting of eigenvectors for T, yeah, eigenvectors for T. Then we can write the matrix T with respect to this eigenbasis. It's going to be diagonal, right? So it consists of lambda 1, lambda 2, etc. Lambda n. So we're again assuming that n is the dimension of the space. and you have zeros outside of the diagonal. So the matrix is like this for some scalars lambda I in F, which is the field of reals. Okay, so this is the matrix we know with respect to such an orthonormal basis beta. But also we have that the matrix representing T star with respect to beta. This is the same as the matrix representing T with respect to beta conjugate transpose, right? So this is by theorem 610. Maybe I won't mention this theorem every time, right? We use it all the time, that with respect, when beta is orthonormal, conjugating the operator of the matrix, they commute these two operations. Okay, so we have this, and since we also have that each lambda I is a real number, right? So we have in particular that the complex conjugate of lambda I is the same as lambda I. So we conclude that the matrix representing T star with respect to beta is literally the same matrix as T, as for T with respect to beta, right? Because we have a diagonal matrix, which take its transpose, it remains the same exact matrix. And then we have to take the conjugate, complex conjugate of each entry on the diagonal, each lambda I, but they are all the same. They don't change when we do it. So we get the same matrix, right? Okay, but if these two matrices are equal, we also get that T star is equal to T, because they're given by the same matrix. Excuse me. And this is exactly what we wanted, right? So it means that T is self-adjoint. Okay, so this gives us the implication from right to left in the theorem. All right, so we get both implications. So this concludes the proof of the theorem. All right, let me know. Oh, I see there's some question. Go back. Yeah, sure. Okay. All right, so we have solved the problem. Yeah, took a couple of lectures, but we have solved this problem. Namely, what characterizes existence of an orthonormal eigenbasis in a inner product space. So this is like a boosted version of diagonalizability, but now on steroids, because now somehow we have this inner product in addition. So we care about basis being orthonormal in addition to just being a basis, linearly independent. Yeah. Okay. So so this gives us the theorem. Oops. Okay. So the next thing, and we'll use it, by the way, you'll see many applications of this. So the next thing we want to discuss is some further special classes of linear operators, which satisfy some additional properties with respect to the norm. Yeah. So this was with respect to the inner product. Now we discuss some properties that may or may not hold for a linear operator with respect to how it behaves in relation to the norm on the inner product space. So this leads us to the following subsection of the class. So we will talk about unitary and orthogonal operators. And their matrices. Okay, so this is the next topic, which, as you will see, is related to what we've been discussing just now. Okay, so we are interested in operators which preserve length of vectors or the norm of vectors. So let's make a definition which makes this idea precise. So let T be a linear operator on V for V an inner product space, okay, over the field of scalars F with dimension of V finite, okay. So we have a finite dimensional inner product space and an operator on it. Then we will say that the linear operator T is an isometry if we have that the norm of T of X is equal to the norm of x for all x in V. Okay, so no matter to what vector you apply your operator, the length doesn't change. The vector, of course, can change, but the length stays the same. So it preserves the distances. Okay, in this case, we say that the operator is an isometry. Now, 2, if we have that the field of scalars is the complex numbers, we will call such T unitary. Okay, so there's some terminology here to distinguish between the complex case and the real case. Okay, so in isometry over the field of complex numbers, we call this a unitary operator. And if the field of scalars is the real numbers, then we call such T orthogonal. Okay, so there are these two new terms. Basically, they're just abbreviations. Like we want to have like a quick way to refer to this property, and also to specify which field of scalars we are talking about. Okay, so let's look at a couple of quick examples that we already know that satisfy these properties. So we have that both the rotation by any fixed angle theta, okay, between 0 and pi, so like in the example we discussed earlier, and also reflection operators on R square, so on the plane, on the real plane, are both orthogonal operators. Right? So this you can see just geometrically, right? Because if you only rotate vectors, like if you rotate if tx by rotation by a given angle, the length doesn't change, of course, right? Because we are only rotating. And the same when you reflect, for example, around the x-axis or something or some other line. If you only reflect vectors, so again the length doesn't change. Just the sign of the coordinate changes, but not the length, not the norm. Yeah. Okay. So these are typical examples. So let's try to understand better properties of such operators of isometries. Okay. So we have the following theorem. This is theorem 618. Excuse me. So let T be a linear operator on V, where V is an inner product space, finite dimension, as usual. Okay. Then the following are equivalent. Okay. We have several equivalent properties. A, we have that TT star, the composition of T with its adjoint, is equal to the composition in the opposite order, is equal to the identity linear operator on V. Okay. We have the second property, B, the inner product of T of x with T of y is the same as the inner product of x and y. Okay. So if you apply T to both coordinates, the inner product doesn't change. So this holds for all x, y vectors in V. Okay. The next condition, C, if beta is an orthonormal basis for V, oh, excuse me, is an orthonormal basis for V, okay, then we have that T of beta, which, remember, if beta consists of the vectors V1 through Vn, then T of beta denotes the set of vectors T of V1 through T of Vn, right? So we have that T of beta is an orthonormal basis for V, okay? So look, this is a property which of course is not true for a general linear operator, because you can, for example, take all vectors in the basis, they can all be sent by T to 0, right? But what we see here is that if the length of the vectors are preserved, then basis goes to basis. as long as it's orthonormal. Okay, so angles are preserved. That's basically the point. Well, that was B. Yeah. Part D, there exists an orthonormal basis okay, for V, such that, and let's say beta for V, such that T of beta is an orthonormal basis for V. Okay, so note in particular, when we prove that C is equivalent to D, what it tells us is that if T preserves some orthonormal basis, then it preserves all of them. Yeah, it preserves the property of being an orthonormal basis. And finally, the last property, E, we have that T of X is equal to the norm of X for all X in V. So that is T is an isometry, as we just defined it. Okay. So we have this list of equivalent properties. So first of all, being isometry, preserving the length. This is E, right? It corresponds to preserving the angles or the inner products. So the inner product of any two vectors, if you apply T to both of them, it still remains unchanged. And it's equivalent also to CD, which tells us that if you take an orthonormal basis and apply T to it, it remains an orthonormal basis, right? And finally, part A tells us that no matter in what order you take the composition of T with its adjoint, what you get is the identity operator. Yeah, so nothing changes if you apply T and then T adjoint. So in particular, because A is one of the equivalents on this list, we get that every isometry is a normal operator, right? So we see that isometries are normal operators, but of course not vice versa. So let me stress it. Okay, so not every normal operator is necessarily an isometry. We will see many different kinds of normal operators, but every isometry is a normal operator. Okay, so we have defined a new subclass of normal operators, the isometries. Okay, but of course we can claim all of this only after we prove the theorem. Yeah? But if you believe it, we have this nice several equivalent ways to describe isometries. Okay, so to prove the theorem, we need to do some work. So today we'll prove a lemma, which will be helpful for it, and then we'll do the proof of this all these equivalences next time. Okay. So what's the lemma that will be helpful? So we have lemma that is needed to prove this theorem. So let U be a self-adjoint operator. Okay. In a finite dimensional inner product space V. Okay. And assume that it satisfies the following. We have that X inner product with U of X is equal to 0 for all X in V. Okay. Then we conclude that U is the zero linear transformation. So U is equal to T0. Okay, which as usual means just T0 is the linear transformation that takes every vector in V and sends it to 0. Okay, so if the inner product with each X like this, XUX is 0, then this is already just the transformation which sends everything to 0. All right, so let's prove this. So we have to distinguish two cases, whether F is the complex numbers or the real numbers. Okay, so by theorem 616, if the field of scalars is C, or theorem 617, if the field of scalars is the real numbers, yeah, depending on which case happens here, we know that there is an orthonormal basis beta for V consisting of eigenvectors for U, right? This is just what we just proved. So U is self-adjoint, so we can choose such a basis by one of the two cases, the complex case or the real case. All right, so we have this, but then if I take X, an element of this basis, beta, then we're going to get that U of X is equal to lambda X for some X in F, right? Because each vector in beta is an eigenvector. So applying U to it, it corresponds to just multiplying by some lambda. Okay, but then we have that the inner product of X U of X. So by assumption, it's equal to 0, right? That was the assumption on U in the lemma. But then this inner product is the same as the inner product of X lambda X, right? But now we can just take lambda out. Well, we have to take the complex conjugate. So this is lambda bar times the inner product of X with itself. Okay. And because X is an element of a basis, beta, so in particular, it is not 0. Okay. So as X is in beta, we have that X is not 0. All right. But then we must have that the norm, the inner product of X with itself is greater than 0, right? Because we know that it has to be greater than 0 as long as for any non-zero vector, right? Okay, but then this equality tells us that lambda bar is equal to 0, right? Because we have here we have 0, here we have lambda bar times something which is positive. So the only way this can happen is when lambda bar is 0. But then this tells us that U of X in fact is equal to 0, right? Because it's equal to lambda times X. But we already just determined that lambda is 0. Okay. And so X was an arbitrary vector in the basis. So what we have shown is that U sends every vector in the basis, namely in beta, to 0, right? But for linear operator U, this implies that by linearity, this implies, so as U is linear, it follows that U of X is equal to 0 for all vectors X and V, right? If it's 0 on each vector in the basis, and it's linear, so it's 0 on every vector in the whole space. And so the conclusion is that U is equal to T0, which is exactly the statement of the lemma. All right. Okay. So this is lemma. As you see it, maybe you can see how it would be helpful, because now we know that if given such linear operator, if all inner products of X with UX are 0, then the linear operator is 0. So in the lemma, we'll be looking at linear operators given by the difference of two linear operators. And from the condition that it's an isometry, etc., we'll often get that the inner product of this difference. So the difference, we'll take U to be the difference of two linear operators, and we'll get that it satisfies the assumption of the lemma. Well, you'll see next time how exactly we're going to use it. But let me stop here today. Yeah, and we'll prove theorem 618 next time. So thanks for your attention. Thanks for coming. Yeah, thanks everyone. So I'll see you next time.